Welcome back to the Innovation by Design podcast. I am once again, as always, joined by my co-host Candace Kitchen. How you doing, Candace?
I'm doing excellent, thank you. And today, our guest is Angelos Chronis. He is the CEO and co-founder of Infrared City, and he's reimagining how architects and planners can use AI in urban design. So, Angelos, can you tell us a little bit about your start, how you came to be, how the company came to be?
Thank you for having me. It's great to be here. It kind of like came about naturally in the sense that this is something I personally and my co-founders have been working on for quite some time. I'm an architect by training. I've spent though most of my career trying to bring technology and the climate together near architecture and planning. So working with new technology mainly to help architects and planners make buildings more sustainable, more performative in terms of the climate. And after working in the industry, in academia, and eventually leading a research lab here in Austria, we developed something that was kind of like a breakthrough. It was really fundamentally new, which is that we managed to train like an AI model that can run a simulation that would normally take a week into a second. And that kind of like led to people wanting to use this. And we made an MVP and we sort of like played around a bit. And then we realized that it would probably grow further if it was an actual company, a software company. So that's why we did a spin-off from the Austrian Institute of Technology, which is where this was born. And that's kind of like how Infrared City was born. It was born from the essentially success of a research project, which comes out of years of research between me and my co-founders and other colleagues, which, of course, I would take the whole podcast to mention.
I'm very curious. It sounds like you were working with AI from the beginning on this. So can you kind of set a date and a time frame and maybe explain the timeline of development of how this, because I think for mere mortals, right, AI is new, right? ChatGPT launched, what was it, 2022, 2023? I don't know. It's only been really on the radar for most people for a few years. Obviously, machine learning has been a part of generative design and in the architectural industry for much longer. And machine learning is a subset or a branch of AI. It sounds to me like you've kind of, like I said, started out with an AI model and running these simulations. But I'm curious, like, give us a little bit of history here.
I mean, I normally call myself an AI boomer because I've been doing this for 15 years. But at the same time, I'm just also new to this because 15 years ago, it was already sort of, it wasn't new back then. My sort of like personal interaction with ML models, with neural networks was when I actually was studying at UCL at the Bartlett. I was under the supervision of Sean Hanna and Alasdair Turner back then. So that's when I first learned as a student what neural networks are, and then I was teaching them for about 6 years at UCL, also at IAC, at the Institute of Advanced Architecture of Catalonia. And if you asked me in 2010 or 2009 if neural networks would be the future, I'd probably tell you I don't think that's going to happen very, very soon. It is true that back then, when sort of like this sort of like DeepMind first results were coming out, with the hallucinations around sort of like puppies and stuff. Like, it was really, really cool times, but it was very niche. It was just for geeks. I mean, I remember sending this around to people and they were like weirded out. I was like, well, what even is this? Like, I don't really care. So back then, I think the sort of like generative design or more computational design was like kind of like edgy, right? Like, we had the beginning of Grasshopper, and I started with generative components back then. The sort of like the ability to design a system of design. So essentially, like, instead of designing the form, designing the system that designs the form, which is what Branko Kolarevic says in his book very, very eloquently. But we had also genetic algorithms or other sort of like, optimization sort of models that were very, very interesting. But like, AI, machine learning, wasn't really that much the case. But I do think that a little bit before the ChatGPT or even the Midjourney sort of frenzy, I think we had already a a big push on AI. So my co-founder, Theodore Galanos, has been working on sort of like architects back then, and like, text to floor plans or GANs quite a lot before even ChatGPT or Midjourney were a thing. It is really, for me, like, every time I walk around and I see AI here, AI there's like literally everywhere these days, and I'm like, I'm astonished sometimes, like, because I don't really even believe it myself that it has grown so exponentially. But I do think that we are also not really seeing the full potential, right? If I say from my side, what infrared has managed to do is really solve the problem that I had like for 15 years. I was teaching CFD, computation fluid dynamics simulations. I was trying to use them. I developed my own solver 15 years ago when I was still at UCL or Foster's, and suddenly I saw in front of me, like, a model that was able to instantly give me a CFD simulation on the ground level of a pedestrian sort of like, wind flow. And I remember the moment. It was really mind-blowing. And I think there's been like moments in others, a lot of us like discovering that an AI model can actually do things that you wouldn't ever expect it to do. And I think these sort of breakthroughs are going to continue to happen left or right. And then they will happen in many different smaller, let's say, bits until we get sort of monolithic, I'm going to spit out a design and the full drafting and everything until the end with just a prompt.
Yeah.
Right.
I want to break down a bit of what you said for our listeners. So you talked about CFD, computational fluid dynamics. And can you just kind of paint a picture of what that is used for in the architectural design space and engineering, actually, too?
Absolutely. It's probably the most complex, let's say, computational model, like most complex model that a computer can run to analyze something. You can imagine it like this, right? You have an urban environment and you have a bunch of buildings, right? And essentially you want to figure out how the air flows through those buildings, right? And the way you do that normally is by discretizing, by chopping up the air into very small pieces, and then try to calculate what happens in between those pieces. It's like voxelizing the space and then calculating essentially how energy, air, and everything else moves around. And normally, if you want to run this properly, you have to run thousands and thousands of iterations of calculations on millions and millions of points. And that takes a very long time. Like a typical CFD takes minimum 8 hours running at full CPU on a really good computer, right? And that's the application of that there can be many different things, right? It can be how much wind falls on a facade of a building, or how much wind falls at the pedestrian level. If you build a tall building, you always have to check that you don't bring too much wind at the pedestrian level, and really it is an unsafe environment afterwards. So all these simulations, we normally have to run them with essentially, these very, very intense computer models. And what we managed to do initially with Infrared City when we first started was actually calculate the effect, let's say, of a tall building on the ground instantly. So it would take less than a second. Actually, we were able at some point, and we still do that, to run it at 30 frames per second, which was like really, it was so fast that you were moving the building around and you would see the wake of the wind. And that for me was like really a breakthrough moment. And that is one of the simulations. Like now we do, for example, thermal comfort or solar radiation or other sort of like all of the different simulations that you need at least at the urban scale. And that's essentially, the big breakthrough for me. The cutting of the time and the effort needed to get to the result.
It's interesting that you say all of that, because one of the things you mentioned was that you were kind of getting high eyebrow raises, like a little bit of skepticism, and you have this great idea. You even have like the model that says it works, but you're still getting people who are skeptical. And so my question is how did you overcome that? And are you still getting that?
I think you always, when you're innovating, right, you always going to get frowns and eyebrows and the rest. I mean, we believe a lot in what we're doing. And I think for us, it's more sort of like we come from years of trying to achieve this. And the fact that we have achieved it tells us so much about what we're doing that it's not really, our primary, let's say, objective is not to convince everybody that it is useful or it is sort of like something that they have to work on. It's just to stay true to our vision of literally making climate assessments and climate simulations as simple as a push of a button. Cool. And I normally want to bring essentially the bigger context around this, right? It's like, why do we need simulations? Why do we need to really understand the climate performance of a building? And I use these days, I pitch this idea around. So I use these sort of like numbers, and it's incredible because 80% of buildings are built without an actual proper climate assessment, and those are the buildings me and you live in, right? These are the buildings that in 20 years will be unlivable, unbearable, and 90% of cities are going to experience severe climate risks. Only 40 or 50% of those have a plan to address them. So there is an urgency that we might not be seeing, in our everyday business life. Like, as an architect, are you really, by regulation required to make sure that your building will perform? Probably not, but it will come, and it will come by necessity.
Yeah. The thing that I wanted to ask you about, and maybe I'll tell a little story to kind of kick this off, because my personal experience with doing CFD analysis on building design came from doing a lab building on a campus, on a college campus. And so lab buildings have, especially, chemistry labs, have what are called, hoods that exhaust all of the gases that students are doing their experiments in. So again, this college campus, out into the atmosphere, right? They're going through filters and things first, but it's very important that the exhaust gas is not being picked up by the building next door in its intake for its HVAC, so normal air conditioning. And so, a kind of personal experience here, sending a model out to have a CFD analysis done by a specialized company to then tell us whether we needed to make changes to our design. And so, of course, you have to make changes because you don't know what the simulation is going to tell you until you do it. Once it tells you, you have information as context then to change your design, modify your design, and do the process again, right? Send it out again. It would take days for this analysis to come back with recommendations, or maybe they didn't even make recommendations. Maybe they just showed us the data and said, try again.
Exactly.
Right? Oh, you're getting closer, you're getting farther, right? So this was kind of a more traditional approach, and we did care about seeing the CFD analysis of the air patterns being, based on the machinery that we were specifying to put in our building, what the buildings in the surrounding context area would be experiencing. Obviously, we can't impact the air quality of what's being pulled into those buildings. And so for you to say now, okay, Candace, I think this leads back to your question, like why were eyebrows being raised? Because it's like traditionally people would just, number one, ignore this kind of stuff, or they didn't know the tools existed because they'd never used them before, or they knew how difficult this was. And when you say you can see it in 30 frames per second and you can move the building around in real time in your 3D model, and you can see the effects of wind patterns as one example, let alone the other types of simulations that you can now do, it's like, no way, that's that sounds like magical thinking, right? And so I'm just curious, like, how AI now plays a part in this, like, how did it go from a week to a second, right? As you said in the kind of beginning of this, because that to me, it sounds incredible that we can have that kind of advancement. And then let me just layer on top of that real quick. Like, you're democratizing this, like you said, to make a push button solution so that when architects and engineers are designing buildings, are making the best decisions when it's the cheapest to make those, which is during design, not later, right? Absolutely. And so then you actually get a much better product in the end. So I mean, take that and run with it.
I have to say, first of all, I really love the example and the insight you have in the topic, because I normally don't have the opportunity to discuss this in such a way, in sort of like in a way that is actually understood. Now, the interesting thing is this, right? Like you describe a case, for example, where we have contaminants, right? And the contaminants can be picked up by another building, and then you're talking about a health hazard. So yeah, there's liability involved. There is sort of like a lot of responsibility. So that you really have to do that there. I remember reviewing. I've done similar sort of like studies. Right? I remember reviewing papers on essentially HVAC design of HVAC systems in an operation room, where you have to make sure that the flow removes the air from the operation room as quickly as possible, so that no bacterial or other sort of like contaminants stay in the room, because of course that's a really important hazard for an operation. And the interesting thing is this, and I if I may, I'm gonna sort of like go a little bit on a sort of like tangent here, trying to explain how this is what actually has driven all of my work from the very beginning. And I'll explain myself. So essentially, you're describing typical in engineering for a lot of problems, right? Like if you're designing a plane, if you're designing a sort of like a boat, these kind of things, like figuring out the flow around the boat, or figuring out how the plane will fly and the wings and all the different things that can happen is a necessity. You do that because you have to make sure that the sort of like whatever design that you're gonna come up with performs the best. And changing the drag on a plane's wings changes, not only the fuel consumption, but if it's going to crash or not. So it's a very important parameter. The interesting thing for me was this, and this was actually the beginning of very early days, like 20 years ago, when I was reading about digital fabrication in architecture, and how we, with the Gary Bilbao sort of like breakthrough, we managed to go from a scrap piece of paper to a full building through CATIA's sort of like, digital project, whatever, really cutting edge technology. And for me the question was always this: we're using the best technology that aerospace engineering or sort of like nautical or other sort of engineering does, and we're only using it to make a form come true, to make a form manifest in reality. What if we could use that to actually make a building that performs perfectly in its environment? And there is this very nice quote I always say in my lectures, which is from Animate Form, from Greg Lynn's book, Animate Form, which is that the ship hull is expecting the environment in which it will operate, right? So in a similar way, the building is designed to perform in a certain environment, and we could be taking a lot more advantage of the building's natural environment and ventilate it, shade it, etc., etc. So like this idea of performance-driven design is what has led my work always. Now, what changes in that significantly with AI? So 15 years ago, again, I was trying to sort of like create my own CFD solver, because I wanted to run 1,000 different options on a canopy so that I can optimize it for essentially its drag. And I kind of did that, but in a very bad way. The ability to run real-time simulation, instant simulations, means you can run thousands or even millions of different potential designs. You can really interact with a performative design space. You can interact with forms that perform really well. And that's what is really groundbreaking for me. It's this ability to explore a whole new world of opportunities that you literally didn't have the chance to do so. If we are going back to your example, right? If you had to send a design and then get a response a few days later with perhaps some sort of like indications, how many iterations can you do? How many different ideas can you test? And that's what's, I think, like really groundbreaking, like this sort of like idea of really vast exploration of performative space. And the other thing, which is how do we do that, right? This is, I think, easier to explain, because what happens with essentially AI, it's not, to be honest, none of this stuff is extremely new. We had most of these architectures or these models already in our minds, like, 10, 15 years ago. But with the advent of computing through GPUs, through sort of like, graphics cards computing,
Video
essentially.
games.
Yeah, so I mean, the GPU computing is essentially, has changed completely the how quickly you can do things. And also, with the advent of like the data essentially regime, that you can have like so much data today stored, used, trained. That's what really makes us able to develop these sort of models. We ran a few thousand CFD cases back in the day when we first did our first model. We've now run more than 400,000 simulation cases in total to train these models with which we are now able to perform the simulations in real time. And that's sort of like the work that we've been doing. We've run a lot of different simulations with a lot of different models, tested a lot of potential architectures to come with the ones that actually allow us to serve simulations instantly. And that is the breakthrough of the AI.
Nice.
Wow.
One thing that is interesting to me about simulations and AI is that it allows the architect, the engineer, to make decisions in real time. Okay, so a lot of times this kind of technology would be used as an output, maybe to justify a certain set of decisions, just like in architectural visualization, right? The renderings would come at the end of a large milestone instead of during.
Exactly.
Okay, so what you're talking about is real-time simulation, just like some other parallel technologies, also kind of made possible by the advent of GPUs, is real-time rendering. And so now renderings are basically free, right? Like renderings used to, like I said, they would take many, many, many hours, not only to actually create the rendering, but to set up a special model just for rendering, right? And so this was a huge process, and now they're free.
Everything.
Basically, real-time rendering technology allows a designer to make decisions with a rendered environment, which is, full materials, lighting, shade, shadow, furniture, entourage, all of these things, and make that their design model, which, let's go back, if we're going to go back and say, design models used to just be wireframe models. Like they weren't even shaded. So we've gone through this evolution. And so rendering technology has now enabled a decision-making process more available to people who are using that kind of technology. I assume it's the same with this. And so I'm curious, like this, again, I used to have to send this over the fence to get something, to get a response. And now you're saying I can do this locally, and I can do it in real time. Of course, hardware, there's asterisks. You've probably got to have some kind of minimum. But most people have this nowadays. Most people have a nice GPU in their laptop, and they can actually just run these kinds of simulations right there. So I'm just curious, like, how have you seen that enable designers to make better decisions in real time? I'm just curious about kind of that topic, because this really changes the game by democratizing this down so that anybody can use it, and they can use it as a decision-making tool during the design process.
Yeah, that's absolutely the point, right? Like being able to run a safety simulation or a thermal comfort simulation or a sort of like energy simulation in real time really allows you to just design something, sketch something even, and then instantly get an answer, right? So what does that do? That allows you to really understand if what you've thought, like, if I put the bedroom in this location and the, sort of like, if I'm talking about a single house, right? Like, and the living room here, how much sort of like, if I put these openings, how much sort of like light do I get, etc. So like you can do real-time daylight simulations indoors, which we're also bringing in very, very soon. So you can also render that, right? And you can see how it looks like. By the way, rendering is a simulation. Rendering is a simulation of light. So essentially, it is the same exact concept. The only difference is that for render, it only matters what reaches the camera. For us, it matters what reaches the ground. Like, so it's actually a render of what the ground sees. Well, with what it is being radiation in the sense of like, for example, solar radiation, and it being a bit more accurate. So if you have the ability to immediately get an answer instead of sending to a consultant or send it to the renderer or the visualization team and then get it back in 2 days, you realize that the openings were not at the right place. They don't look as nice from the living room, but they also don't perform as nice from the living room. And then also, where wind is a lot more complex, you don't even normally understand how it works. They also don't work well with the natural ventilation concept that you had in mind. Then you can very quickly do changes. So there's a few things that happen there, right? One is, first of all, you start educating yourself. You start understanding, if I do that like 10 times myself as a designer, if I move the windows in the wrong place for natural ventilation to go for the sort of like cross ventilation sort of concept to work, then I realize that I should not be doing that. So that's one of the things that are happening. The other thing that happens is that you can start putting in helpers, putting in sort of like agents that can figure out things for you, where you say, I care about the daylight in this space and I care about the wind, the ventilation, but I also care about having a view to the sea. So can you just go out and like bring me back 20 solutions of where the windows should be? And I think the question that I always had when I was sort of like in the beginning of my career, like doing computational design models, was, okay, are we going to replace the designer? The exact opposite. We're going to superpower the designer. We're going to allow the designer to send his virtual assistant or her virtual assistant, get back 20 windows options, and then really get the intuition back in and be able to select things. And then on top of that, you can probably, of course, optimize things. You can actually, we've done things like, for example, reinforcement learning, sending a tower around and it finding its space so that it minimizes the pedestrian wind comfort and maximizes the view. So you can also just use the machine to just solve problems, small problems, which, by the way, would be the exact same idea as the one you were mentioning before, which is essentially figuring out where the sort of like hood should be so that it doesn't contaminate the building next to you. So where does that tower need to be so that it doesn't cause an annoyance on the ground? It's kind of like just a mini solver, a small solver, which is part of your overall design concept. The design concept is still yours.
I think what's interesting about that too is that that superpower that you're talking about is that it's actually cross-referencing lots of different things. Because I think as a designer, I know, okay, I make this window bigger, it's more pleasing for one reason, but it has other ripple down effects, right? It's going to let in more solar radiation if it's bigger. It's going to change, it's going to cost more. There's these different variables that you're triggering that aren't like, they're not top of mind because they're not all linked together in real time. And that to me is really the superpower, especially with these agents, is that one agent can go talk to another agent, can go talk to another, and they can cross-reference materials to give you a solution that you can then justify across many dimensions, right? And that to me that's super important because I have a lot more information to go off of, especially when I'm talking to a client and say, well, client demands something and it's the architect's job to respond to that. And that response may not be give them what they want, because now I can actually point at the data and say, here's what that actually means. Here are the unintended consequences of making a decision like that. And here are the benefits. And now you can actually make a decision based on data. And before, I think that used to just be intuition a lot more. And now it's really interesting to see that shifting more to data-based justifications.
Absolutely. So, what we're trying to do, we normally say there's like three things in what InfraRed is and how we're trying to give it to our users, right? One is these models. The models can be very powerful. It means I can really take a sort of like 3D model and I can run a simulation in 1 second or less than 1 second or like in a minute if it's a very complex one, instead of like 3 days. That's one thing. It's very important. The other thing is, of course, integrating that. It's essentially, where do I, if I have to actually create a new model for this, then it's not very useful. I let's say, design in my CAD software, I want everything to be in there. So we've made infrared so that it's completely open to integrate as an API and everything. You can actually just directly ingest it. But the third, which is I want to talk about more, the third part is explaining those simulations. The typical sort of like response that I would normally have is like, okay, so I can, let's say, get the simulation instantly, right? And I can see the pretty colors. What do I do with them? And as you say, you know, I remember a paper from Son Hanna. I always remember that paper where he was mentioning architecture problems as wicked problems, problems that you cannot optimize because they have multiple objectives, multiple layers. You change something, you're breaking something else. You're fixing something, you have to adapt something else. So it's sort of like these sort of multifaceted problems that you can never have. There's not even, I think, Pareto fronts. Like there's not sort of like optimal solutions. You have to really find your space there. So explaining what a simulation is for us very important. So what we've done is we have this very powerful physics models, right, that can calculate things very fast. But then we've also trained our agents to take these models, take the climate data from the location, take other sort of like data from that site, and then take the regulations in from all the different sort of like or guidelines and regulations in from all these sort of like different organizations, and then essentially give you a report. I give you a written description of the project, of the climate, of the exact solution of the specific design that you're having and how that works or doesn't work, which is the first step towards orchestrating a much more sort of like interesting approach. So essentially, if for every design that you give me, I can actually give you a full report back in a couple of minutes, you can give me also 100 designs and I can give you 100 reports. And then you can ask another agent to go through those and give me back from all of these 100 different options, the sort of like overview, the high level, let's say, metrics of most of the designs. If you start putting towers in the front of this waterfront, you normally introduce very high winds, and then that means that you cannot have essentially a plaza around it that it's going to perform well. If you put vegetation in the front, all of the other 50 options have vegetation in the front, they always perform better. So put your towers in the back. That sort of insight would normally take you a few different design cycles, discussions with others, and I think that's where it gets very, very interesting.
Yeah.
I love that you're talking about data right now, and that was actually where my question was kind of going. And maybe I'm getting ahead of myself, but I imagine that as you continue to do this and as you continue to do more and more projects and different climates and everything like that, the data that you can collect and then understand, and obviously everything is going to be different, but eventually used to optimize, I can only imagine. I mean, it kind of feels like it's pretty limitless with everything that you can collect.
Absolutely. I mean, we have a pledge that we say we're not going to use users' data to learn things so we don't want to use the users' data to actually learn how to help them design, but we do lots of synthetic data sort of like exercises where we try to generate thousands and thousands of different cases so we can then understand and then even annotate those, or like kind of like go into optimization processes. But I love the question in the sense that it is incredible how untapped design data is. Right now, if you had an architecture practice that was sort of like working for 10 years, the amount of CAD models that you've produced, the amount of analysis that you've produced is insane. Yeah. It's like really so much data that nobody uses. And there is an even worse. I actually wrote an article about it. It's called Cities as Data Machines. It's essentially that cities themselves have the most unused data in the world. Like we're talking about daily producing, humongous amounts of data from every city that nobody really uses because systems are not there. So one of the amazing things about AI is actually its ability to work with also unstructured data, with data that's fuzzy, data that's missing stuff. So you don't have to have like everything in that row filled to be able to understand something from it. And I think we will see in urban data, we will see a breakthrough of solutions. There's so many happening right now. There's like, I'm also teaching at IAC, and I see what students make in a couple of months by tapping on data and AI models that are really cutting edge. It's really, it's moving so fast.
You talk about kind of communicating information, right? Because like a simulation is usually kind of a color-coded thing that you're looking at, and the colors mean something. And there's typically has been, especially in kind of climate situation type software, it's like, here's the data, and then the designer could interpret that data. Like they have to learn how to read it, right? And so I think what's super interesting about what you're talking about is that these agents and the narrative that can be generated from that data can actually explain it to you, but it can also explain it to you like you're in the fifth grade, right? For example. And I think that is super interesting, because an architect's job is then to communicate that to a client, and a client doesn't speak architecture, right? They speak whatever industry or organization they're in. It could be finance, it could be real estate, it could be education, whatever. And so, architects, as one myself, I know there is a vocabulary that goes along with architecture, just like there's a vocabulary that goes with any other kind of industry that you might be in. And our job is, again, to communicate to that client in a way that they understand, so that they're making the decision for their organization, and it's thoughtful, right? And that it really isn't just like, oh, that sounds good, I guess we'll go with that. It's important. And so what's really interesting about large language models then, on top of the data that you are simulating and then presenting, is that you can actually explain it to somebody in a way that they can understand it and learn from it and feel good, like not just feel good, but feel like they have a better understanding of this. What do you see happening with kind of that's like a democratization at a different level in technology?
Yeah. It's well, my mind is going all sorts of different places. So I have like my own synapses firing up right now with what you said, because I can go in many directions, but I have one that I'd love to touch upon. So you said earlier, right? Renders are the first, like they're the first ones that we saw sort of like being revolutionized by this idea of, I have a model, right? An architect thinks, I at least think like that. I can think of space in a very detailed way. I can probably model it up to a certain point, but then when I have to visualize it, I have to really put some effort in like explaining the view to my user, my client, or whatever. We normally sell these images, right? The way we sell a design, we say, look, this is going to look a little bit like this. You're going to be sitting on your living room, and this is what you're going to be seeing. This is sort of like all the different nuances of the different sort of like materials and all the different lighting or whatever, like all of the stuff that you put in, and that's the design component, right? You're selling an experience. You're selling to someone like, this is going to be your living room, and for many, many years, you're going to be looking at that sort of like view. So that's what I've built for you. And it's very, very interesting, because we normally do not sell like all the other information about the house, right? It's essentially, how much noise will the washing machine make if you put the washing machine very close in the kitchen, and then you're sitting in the living room watching a movie, or whatever, right? Things like that. So what about the climate even worse? Like, so if I was to tell you that, this beautiful balcony that you're building, or this sort of like terrace that or this sort of like big plaza that you're building is not livable, it's not sort of like walkable in 20 years, then people would really change their narrative. And what you're saying is essentially, how does this sort of like LLM idea, make these concepts more explainable? If I was able, imagine like, I come to you as an architect, right? And you don't just give me a view. You don't just give me an image of like, this is how your living room would look like. I can query that living room, and I can ask it, is it noisy? Imagine as if you're going to a sort of hotel and you're reading all the reviews. You say, is it noisy? Is it sort of like, is it very hot? And it's like, and then that model can tell me it's unbearably hot in the summer. You can't really and then I'd come to you as an architect and say, excuse me, your model is telling me that it's not going to be very, very good. And I have this amazing example. I was I live in Vienna, right? I was looking for a place to rent, and I found this beautiful sort of flat in front of the canal, right? And the sort of like the Danube Canal that crosses Vienna. And it was in front of it. And then I was looking at it, and I was like, okay, this great view, okay price. And then I realized there was a bit of noise. And then I wanted, as a sort of scientist, to check the noise map of Vienna. And I found that this was the hotspot of noise in at least the central Vienna. And I was like, okay, that doesn't sound good. What does that mean, right? And then I started looking at papers, and then I realized that 10 decibels more at night when you're sleeping kill you 5 or 10 years younger. And then I freaked out. And I was like, why don't I even know anything like that about anything that I'm building or anything that I'm buying or renting? And this is where I think it will get very, very interesting, because especially with climate resilience, which is what we're trying to do, is, there's a huge opportunity to start explaining to people that they're not just buying a flat, they're not just buying a piece of land, they're buying a refuge for the future. And that refuge has to be performing. And that's where I think, making these sort of very complex simulations, very complex analytics, digestible to a sort of lay person, right? Then it will have a significant difference in how we actually value property, how we value land in terms of its impact and its resilience capacity. You're buying today square footage and the view and perhaps how close you are to the metro. You have to also be buying daylight availability, natural ventilation potential, energy when energy grids crash, and essentially all of the other components of a building. And I don't want to paint the entire picture, but I just think that this is one of the very important things that AI can bring to design. This added value information and a shift from the sort of pure economic value to this impact component.
I love this idea, and this is totally new to me, that what you just brought up, which is, because as architects, we've talked about the client being a co-creator in the process, but it's super limited, right? It's like you can walk around your model, you can tell us what you think of these views. We can put a floor plan in front of you, and you can say, no, move this over here, but we don't really know how to read floor plans, right? From a client's point of view, there's all kinds of limitations in kind of this back and forth. But for a client to be able to kind of interrogate a model, because there's data in the background with simulation, with climate, with all kinds of things, right? Materials, VOCs, daylight. There's so many different aspects to it. If that data is live and kind of plugged in and queryable by a client, it really kind of changes the narrative, which is what's really connecting with me right now, about a client's ability to be a part of the process so that we can make those decisions once again when it is the cheapest to do so, which is when it's still in the computer, right? It's not on the site, because I think there's implications for what you're talking about for the built environment as it exists today as well. Like your example of the flat on the canal, right? It's like, oh, there's stuff that I didn't notice when I visited it at that particular time of day, at that particular time of year. That's what's interesting about real estate, right? Is you're going to go visit houses when you're trying to find a place to rent, and it's like, oh, it's perfect. And then, 3 months later, it is absolutely not perfect because that time of year, something else happens that you weren't aware of. But I think, again, kind of bringing this decision-making and collaboration process to the earliest part of a project to make those decisions as the best we possibly can. It's at a whole new level of the best we possibly can than it ever has been before. I think that is what is a really amazing takeaway from this conversation.
If you look at numbers, 20% of the design time is the the sort of like time that where everything more or less gets decided that affects the climate performance of the building. And I have to maybe add one thing here, if I have at the time, is, when we're talking about I'm buying my own flat, or I'm sort of like, investing on a building or something like that, then it's a very personal sort of like concept. I have to make sure that for whatever parts I care about, because perhaps I'm a climate change denier and I don't really care about, all of the things that you're trying to sell me. I know I'm going to use air conditioning, so I don't really care. So I want the view and everything. But when we're building a square, where we're building it for the road, like for everybody, right? When it's like a common good that we're building, when it's essentially something that we all together own, this idea of sort of like let's say concession, right? Of like the idea of like being able to agree on what we need and what we don't need and what we care about and not, is hugely important. And the problem, I always bring this example. I was at Barcelona when we did the first super blocks, the first super block pilots, like in pedestrianizing like these 3x3 sort of quarter 3x3 sort of streets, and making essentially pedestrian space out of what was a street. Everybody hated it. Like they wanted to really park their car in front of their house and let's go up and like with the grocery. And everybody hated the project. And now it's a very lively space, etc. So I never really understood how it is possible for someone to like not really want their, street be pedestrianized and like be much nicer, have like, trees and everything. And I believe that what we're missing is this information. What does it really mean? And I'm going to give you the most sort of like, uninteresting example for me. Land value. How much does your own building or your own sort of like house go up in value when you do that pedestrianization, when you bring that sort of like greenery in? Not to mention the health benefits that you might have, or sort of like your family might have, or like, and that's why I think like I do believe AI can democratize a lot of that data, a lot of this information, and that's exactly what we're trying to do, to democratize the information so that you can actually make informed decisions, informed participation in decisions. When you're, asked by your municipality whether you want A or B, you're able to understand why you want A or why you want B. And I hope that this sort of democratization of data in design can lead to a shift in what we care about the most. Because we've gone through an era of iconolastic sort of like, design. And I think we can go back to an era of let's make sure that the data actually works and that the building actually performs.
Yeah, the trade-off from, because you're right, like if you're representing a larger body of people for decision making, accountability is super important, but also like making sure you're addressing all of the concerns in the best way that you can. There's never been easier to do than now, because you can take that input and you can synthesize it in really interesting ways. But also you're talking about like the future benefits that's something that's hard for some people to grasp, right? And it's like, well, you're taking away my convenience now, and you're saying in the future it might be like this, but actually having the data to back that up, to tell those stories so that people feel reassured in those kinds of things, could completely shift the way that you move forward on a project. So fascinating conversation. I really appreciate you coming on the podcast to tell us about this. This is fantastic. And it makes me very hopeful about kind of where technology is enabling designers and architects and engineers and contractors to go, so that we can have a better built environment.
Absolutely a pleasure to be here, and thanks for having me. And I share that hope. I do believe we can all contribute to a more sustainable future for architecture and design.
Absolutely.
Excellent.
So we'll have links to everything that Angelos talked about in the show notes
amazing.
for this episode, so people can check out more and do a deeper dive into what he's been working on and some of the terms that we brought up that you maybe didn't recognize. So we'll definitely put as much as we can in there. Candace, any parting thoughts here?
It was an excellent conversation. Thank you so much, Angelos. I'm interested in learning more about your company and seeing where it goes. So thank you.
Thank you so much for having me. And feel free to reach out, everybody. I'm here for all the different questions you might have.
Nice.
Awesome. Thank you.